Okay, well, it's my great pleasure to again introduce Xiaoxing Xi, who, as many of you heard, gave quite a, well, disturbing colloquium yesterday. But we're also very glad that he's going to give a scientific talk today. And so he'll be talking about tracking the nanophysics of oxide interface and heterostructures with atomic layer by layer laser MBE. Thank you.
Well, thank you, Jeremy, again. And I really appreciate the opportunity to come here to talk. And I do want, as I said yesterday, I do want to talk about my experience because I think that's important for the community to be aware of this and speak up for the interest of the scientific community. But I have to talk about my science too. And so, you know, I would risk overstaying my welcome and give you another talk on the science that I've been doing. And this is very much part of the reason I moved from Penn State to Temple in 2009, because I want to do this thing that we call atomic layer by layer laser MBE. So, you know, I would talk about physics, which has a lot in common to what Jeremy has been doing in these oxide interfaces. And but I think I would be quite heavy in technology, techniques, because I think this is something that is useful for many studies of physics. And so first I would like to acknowledge the contribution from people in my group, my former postdocs, students and postdocs, and also we collaborated with many groups, both at Temple University. Alex Gray is a ARPA's person, and our new hire, whom we are very glad that he joined us. He does the X-ray spectroscopy. His contribution is very important to this work. And we also work with many people from other institutions. The funding is mostly from DOE. That's on the oxide superlattices. The Lansam Nicolate work was funded by NSF grants. So for the first part of the talk, I want to just address this issue that the advances in nanoscale engineering of oxide interfaces and heterostructures have led to discoveries of emergent phenomena and new artificial materials that has been the focus of condensed matter for many years. And so in late 1980s, when high-density superconductor was discovered, people did not know how to grow epitaxial oxide films. And there were, so a lot of efforts were put in it, and that was the time when pulse laser deposition was invented, which has the advantage of pretty much reproduce the composition in the target in a substrate that's very useful for multi-components, multi-element oxide materials. And so that's a huge step in terms of technology of depositing epitaxial oxide films. And now and then later in the 2000s, then people have made the progress such that you can kind of make these materials one atomic layer at a time, and in particular in the oxide MBE that is allowing people to do a lot of very interesting science, right? And again, here I'm showing that in the early 1990s in high-TC superconductor, the group that I was in at Belcore and Rutgers, we were growing these YBCO, Praseodymium BCO superlattices. At that time, it was very very important progress. And then in 10 or 20 years, then people could grow these barium-tiny, strontium-tiny superlattices with all these superlattice peaks and very good crystallinity and stoichiometric control. The two most successful techniques, one is, are shown here. One is the reactive oxide MBE. This is taken from Daryl Schlom's lab for a reactive oxide MBE. And you have different sources of elements and UHV environment. You have read monitoring of growth, and that's proven to be able to grow very high quality films with great perfection of crystallinity. And the problem is that there are limitations that they can only operate at the low oxygen pressure. They can use ozone, but still that's limited to low oxygen pressure. And also, all these metal sources have to have some kind of a similar properties in terms of if some elements want more oxygen and some hates oxygen, you cannot put them together. And also it's limited to you cannot use this for some D and F, the F electrons, the elements and so on. And pulse laser deposition is another technique, or laser MBE is a sophisticated version of PLD that does pulse laser deposition under the MBE condition. And it's more versatile. You just shine the laser on the target of materials you want to deposit film, and that generate plume and deposit on the substrate. And it can be used for many materials, and it can work with a much broader oxygen pressure range and much more versatile. The problem is that people found the stoichiometry, although you can roughly reproduce the target stoichiometry in the substrate, it's not exactly the same, and it depends on the growth conditions. And there are other issues like, for example, the energy of the fluxes are higher than in the case of evaporation. But these are the two most successful techniques in making oxide films. And here is the examples of physics that all this capability allow people to do. Barium-tiny, strontium-tiny superlattices. This is a TEM image of a cross-section sample. And you can see that these are precise to the unicell level. And so you can grow very high quality samples to study the properties like ferroelectricity at the nanoscale. And this interface properties between lanthanum aluminate and strontium titanate is an excellent example of the new physics at the interface, where you put two insulators together, and then you find that under certain conditions, you find a conducting 2D electron systems at the interface. And so that's what Jeremy has been working on. A lot of very interesting stuff, and also a lot of many other groups has been working in this area, made possible by the capability people can grow these high-quality interfaces. The other example is in the lanthanum nickelate, and there is a theory that predicts that if you sandwich lanthanum nickelate between some insulator like lanthanum aluminate, you could actually separate the degenerate d orbitals at the Fermi surface to make the materials to have electronic structures similar to high TC superconductor. So if you dope it, you might be able to build a high TC superconductor from the system. And of course, there are many theoretical and experimental work. For example, people pointed out that actually you do have the charge transfer between the nickel d orbital and the oxygen p orbital that make this kind of orbital polarization much less than what this original theory predicts. But then there are people who are suggesting different kind of heterostructures. For example, put some insulator here to prevent this charge transfer, and in the hope that you might be able to create an artificial high TC superconductors. Of course, if you want to do this, you would have to have the capability of growing these materials really in the atomic layer by atomic layer level. So what I'm trying to tell you is the technology we have been working on since 2009 that's combining the strengths of reactive MBE that I've shown you, and also a PLD. And we're showing that this technique, we call it atomic layer by layer laser MBE. We believe that it significantly advances the state of the art, that extend the capabilities that we have to make new materials, to make higher quality materials. And we believe that this will have a large impact to the technologies of making these heterostructures and interfaces. And most of the work is published just recently in this MPJ Quantum Materials, and earlier this year. And so that's what I'm telling you mostly in this talk as well. That I will talk about this technology, and I will use the examples of materials like a Rhodothan copper phase, lanthanum nicolate, like a lanthanum aluminate on strontium titanate, and then also on the metal insulator transition in lanthanum nicolate, just to demonstrate the powerfulness of this new approach. So here I show the atomic layer by layer growth versus unicell by unicell growth. We've seen this from oxide MBE, that you have different sources, and then you can open the shutter alternately so that you put down one atomic layer at a time, versus the conventional PLD or laser MBE, where you take a target of the materials that you want to grow film of, and you just shine laser on it, ablate the materials. In this case, all the elements come together. Right? They actually grow unicell by unicell. Then you use a read intensity. You monitor the oscillation that reflect the roughness of the surface. And when you have a half unicell grown, the surface is rough, so the read intensity goes to a minimum. And when you completely cover one layer, it becomes more smooth, and intensity goes to the top. And so, as a matter of fact, the read intensity reflects both roughness information as well as the chemical information, because of different scattering cross-section. But in this case, of course, all your elements comes together, right? So that kind of that averaged out the elements due to a different the information due to different elements. And what we have been pursuing is to use separate target. Instead of strontium titanate, for example, we use titanium dioxide and strontium oxide target. And we just switch the target in front of the laser back and forth, so that on the strontium titanate substrate, we first put a strontium oxide layer, and then followed by another titanium oxide layer. And because all these different elements come separately, so these, the intensity of the read spots reflect both the chemical information as well as the roughness information. Right? And with this, we could monitor the deposition so that we can cover the whole layer, atomic layer of strontium oxide before we switch. Yes.
What's the time scale for this oscillation?
Well, it's you will see that in these slides. Here are seconds. So we use like a 1 or 2 hertz of pulses, and it takes about 100 pulses to grow one atomic layer. About roughly in the order of 100 laser pulses per one atomic layer, and we run it to 1 or 2 hertz repetition rate. And this is very similar to what MBE people are doing by opening up different shutters, except that here we are using the laser pulses. And the same way, exactly the same way as what Shalom demonstrated, that you can monitor the read intensity oscillation to control whether you have one-to-one strontium to titanium, or you have too much strontium, or you have too little strontium. And so that can help control whether we have the right ratio between the two elements. And also, just imagine, even if you have the right ratio, if you are not covering the whole layer, or let's say you covered 90% and then you switch to another, when that happens, you will have this kind of beating. And if you have completely covered one layer and then go for the next layer, and you have these stable oscillations in the rate intensity. So with this, we can control the, so let's say we have about roughly 100 pulses for each atomic layer. So you can control it to a few percent. And this is obviously, sounds very good, but actually in reality, even for MBE, that's not the only thing you rely on. You rely on everything, right? And including the calibration that you do. Right? And so you would make samples and then do the X-ray diffraction and measure the thickness, X-ray reflectivity, X-ray diffraction, see all the peaks to determine the deposition rate. And then you go back to grow and so on and so forth. So you need everything. Here I'm showing that some situation when you start from half monolayers of strontium oxide, and then followed by one-to-one ratio. So obviously you start from half unit cell, and then you add more. That's not stoichiometric to start with, but you are following up with stoichiometric supply. And because it's not stoichiometric, you see this kind of a complicated multi-peak features. But if you follow with the stoichiometric supply, this complicated feature is being reproduced. And the way I'm showing this is because rather than using up and down and up and down to monitor, we use this kind of a complicated thing to monitor. So it gives us some more sensitive ways to calibrate whether we have grown one atomic layer or off stoichiometric. And so basically you use all of these together to calibrate the deposition, and then during the deposition you follow this pattern. And with these, we are able to grow materials one atomic layer at a time. And strontium tinnate is a prototypical system that you can use for this technique. We've grown films, for example, with the different stoichiometry. And from the RBS, we can measure the stoichiometry from, compare that to what we designed it to be. And here shows that the lattice constant, C lattice constant, as a function of the composition. And it is known in the field that if strontium tinnate stoichiometry is off from 1-to-1, you actually will see the expansion of the unicell. And here I show the result from laser MBE and the reactive MBE from Daryl Shalom's lab. And we found that the two techniques gave very similar results. And X-ray diffraction is to look at one of the peaks. This is from the substrate. This is from the strontium tinnate films. You'll see that if it's off stoichiometric, you will see the film peak that's different from the substrate peak. And when they are close to stoichiometry, you cannot really distinguish them. And this UV Raman also shows that the symmetry breaking is minimum when the stoichiometry is achieved. So this is strontium titanate. We've demonstrated that also in calcium manganoids and barium titanate. And so the technique is quite versatile for different materials. And these, of course, are materials that are neutral. And we have also used it to grow these polar materials like lanthanum nickelate. And we've grown lanthanum nickelate, this rather thin popper phase with different ends, right? So for this phase, for n number of perovskite type of layers, one more lanthanum oxide layer is added in it. And people have been successful in growing n equals to 1, 2, 3, but nobody has reported n equals to 4. And from the phase diagram, you can find that if you want to grow higher n value, you need higher oxygen pressure. The problem is, every n perovskite layers, you want to add one more lanthanum oxide layers. But when people go to higher oxygen pressure, very often people cannot maintain the atomic layer by layer growth. So nobody has reported this earlier. But we use our technique. We have shown that we can grow this material. And the deposition pressure we use is 37 millitorr. And it's high enough to allow the phase to be stabilized. And but our technique allows us to go to this high oxygen pressure and still maintain the layer by layer growth. And here, actually, we shaded this the intensity oscillation. So you can see that for every 4 1-to-1 deposition, this area of this time for lanthanum oxide just extended for some more laser pulses to add another lanthanum oxide layer. So we were able to grow the right phase, and the TM shows that that we got indeed every 4 layers we add one more lanthanum oxide layer. So I'm using this to demonstrate that this atomic layer by layer laser MB allow us actually to push this thermodynamic boundaries further to the areas where otherwise it's not stable. So the first example, which is mainly what I'm going to tell you about today, is this lanthanum aluminate strontium titanate interface. And by growing lanthanum aluminate of different stoichiometry, and we have demonstrated that the electronic reconstruction picture is able to explain the two-dimensional gas behavior at the interface. So if we look at this again, if we grow lanthanum aluminate on strontium titanate, then we have a problem that that in the lanthanum aluminate layer, there will be electric field that would diverge. Right? And if it is on titanium dioxide terminated layer, it diverges positively. And if it is if it's a strontium oxide layer, it diverged negatively. So to deal with this, for the titanium dioxide termination case, you would transfer half of the electron to the interface. That's proposed to be the origin of this 2D electron gas system. And if you do have that happening, what you can expect is that you will need 4 unit cells of critical thickness. Before this transfer takes place, you have to offset these band gaps so that you can have the transfer. And after that, you will have a gradual increase of the carrier density. And eventually, you would have these transfer of half electrons, which would translate it into 3.3 times 10 to 14th electron per centimeter squared. At larger thickness. So how much electron is being transferred to the interface depends on the thickness. Right? And the critical thickness has been observed by many, many groups. And this gradual increase has never been observed by any group. And many groups has the problem that this number is not right. So that's what I'm showing in this slide, on this slide, that the reported carrier density in the literature are too small. And this work, for example, has this abrupt change to something like 2 times 10 to the 13th. And this is, again, the slides that I showed earlier. This is what predicted by theory. But these are the data points that people get, they got from the experiment. This is a work that actually studied the change of stoichiometry in the lanthanum layer. They do see a dependence with a different composition, but all these values are still off from what people would expect, 3.3 times 10 to 14th. So the problem is that when people grow lanthanum alumina layers, they cannot grow the materials at high oxygen pressure because you will not be able to grow the film still layer by layer. Because of that, people have to grow the film lanthanum aluminate at low oxygen pressure. And it is known that strontium titanate loses oxygen very easily. Right? So if you grow the materials at low oxygen pressure, this is the scanning of the resistance mapping. And you can see that the substrate very much contribute to that the conduction. And so what people do is to anneal the sample at higher oxygen pressure after the growth to try to fill oxygen in. And then when they do that, they do see that the conduction layer happens at the interface. But the problem that I would claim is that annealing oxygen to fill oxygen back into this interface layer after the growth is not the same as you grow these materials with oxygen stoichiometry. Right? And that is something that I think is causing the problem for all the previous reports. So here I summarize the results that in the literature. Here shows the oxygen pressure during the growth. And some of the paper has the post-growth annealing, some did not. So if you grow it really at the low oxygen pressure, and you can see very high carrier density, which you know is not from the interface alone, but has oxygen loss in the substrate. If you have annealing afterwards, then you bring it down. Here it's 7 times 10 to 13. Still not what the people would expect to have, right? With the annealing, you bring it down, but it's not what you expect. And this is true for other conditions as well. The highest oxygen pressure used during growth is 10 to -2 from the Geneva group. And so 2 times 14, that's about close. But still, when they annealed it, the oxygen the carrier density actually goes down. And there are other papers from the group that shows that they actually is very much random. So that's, I believe, is well, not many people talk about that. But of course there are theories to explain why they have this not consistent with the prediction. And of course, partly due to that, and also, just from the skepticism of the whole thing altogether, there are other mechanisms that have been proposed, like oxygen vacancies in strontium titanate and bombardment of strontium titanate. When you bombard it, it becomes conducting without even the top layer. And then there are proposals of interfacial mixing between the lanthanum aluminate and the strontium titanate. People know that when you dope it, it becomes conducting. And so this area, the mechanism of this 2D electron layers is not, that there's no consensus about what is really causing that. And I think it's an area that sometimes, whatever you say, some people will not be convinced that this is, some people believe it's an oxygen problem in the strontium titanate. Some just think it's the intermixing and so on and so forth. So there are all different kinds of works and trying to understand the mechanism. This is an example that I want to show that from the Geneva group who dilute lanthanum aluminate with strontium titanate. And so when you dilute, you grow the mixture of lanthanum aluminate and strontium titanate, what you do is to change how much charge is in each of the layer. And if you just grow lanthanum aluminate, you would have each layer carry either +1, -1 charges, and then the field diverge when the thickness increases. But if you grow the diluted film, then each layer is carrying only, in this case, it's 50-50, lanthanum aluminate versus strontium titanate. Then it carries half, +half, and the -half of charge. And the divergence of this field become slower. So this will lead to different critical thickness, which this report has observed. Right? So that's good. That is kind of supporting the idea that you do need this divergence and to get the 2D electron gas. If you do look at the carrier density for different thickness layer, though, you'll see that it's kind of a random. It doesn't really show systematics, and the value, this is 10 to the 13th. And let's say if you have a lanthanum aluminate layer 10 unit cell, you will get something like 5 or 6 or 7 times 10 to the 13th. So it's random. It's not systematic. And number also does not really match what people expect. There have been work that are trying to change the stoichiometry of lanthanum aluminate. This is the work from Daryl Schlom's lab using the Oxide MBE. And they can put, they could put many substrates there, and so that you can grow the materials with different stoichiometry. And the green one is the conducting samples, and the red one is insulating samples. And from this, what they have seen is that stoichiometry is important. Right? All these films are grown under same nominal growth condition, except that the composition is different. And you can see that aluminum rich is important for having this conducting layer. That's what that paper concludes. And there's paper, this is from Lynn Martin's group. They also study the oxygen stoichiometry. And here is from Harold Huang's group. And in each of these cases, they change the stoichiometry by changing the laser energy density. But you are changing the laser energy density, so the bombardment situation is different, and the properties of the film is not just the difference in stoichiometry. So these are the works that one can find in the literature that studied the effect of stoichiometry. So our work. We use the technique that I introduced to you, this atomic layer by layer laser MBE. And all the works that I'm going to present is 10 unit cells lanthanum aluminate. And we grow them at 37 millitorr. There has never been report that can grow these materials layer by layer and still conducting at this kind of pressure. As I said earlier, the highest pressure reported is 10 millitorr. People ask, why don't you go even higher? When we go even higher, even we cannot maintain it grow layer by layer. Right? In this case, though, if you look at this read intensity oscillation for 10 unit cell, we maintain very nice oscillation of the read intensity. the pattern shows very nice films, and AFM also shows smooth films. And this is starting from the titanium oxide terminated substrate. And the very first lanthanum oxide layer gave us these down, up, and down kind of feature, which I think reflect the fact that we are transitioning from this substrate and to these films. And so we don't know how to explain all these features. But once we have this aluminum oxide layer, and then everything starts to grow very regularly. Yes?
So do the targets themselves bring oxygen? Or, I mean, is that one way? Because if I think about this like hybrid MBE that Suzanne Stemmer, she has these precursors which bring oxygen to the substrate. Is that happening here, or is it just you're able to just grow at higher pressures and that's why you have better oxygenation?
I don't think there is a simple answer to your question, because during the pulse laser deposition, there are all kinds of things in the plume. And that's something that I think one has to think about. What's happening? You have molecules, you have atoms, you have ions, you have all kinds of things. And how can that all organize themselves to grow layer by layer, either neutral materials or polar materials? I don't know. I think I would very much like to work with some people in understanding what's going on. So it's not a simple answer. There are molecules, and there are also non-molecules. There are charged and there are neutrals, everything. And so basically, what I'm showing here is that we could grow layer by layer at this very high oxygen pressure that nobody else could do. Right? And the consequence of that is that we think this condition allows us to grow these interface without oxygen vacancy. Well, I cannot say without oxygen vacancy. I can say that oxygen is much better oxygenated compared to people who grow the film at low oxygen pressure. And we use, there's no good way to measure oxygen vacancies. And what we have done here is this X-ray linear dichroism which people have shown that, for example, in this work, people have shown that if you grow the film at low oxygen pressure, 10 to minus 4 torr, you'll see these titanium 3 plus peaks. And if you anneal it at 200 torr oxygen, these features go away. And what we have done is different composition films, and grown using our way, 37 millitorr, and we don't see this feature that people attribute to the oxygen vacancies. Right? And so what one person asked me about whether you are sure there's no oxygen vacancy. All what I'm saying is, in the sample that we grew, we do not see the signal that people attribute to the oxygen vacancies. Right? It's similar to what people have after they annealed it at high oxygen pressure. This is the result of X-ray magnetic circular dichroism. And again, this is from the same paper in the literature. They have shown that if you grow it at low oxygen pressure, you'll see this kind of signals. When they anneal it at high oxygen pressure, and the signal becomes weaker. That is from our data. And so these you can compare these scales. That all our samples are showing much weaker magnetic signature in these samples, which we believe is indication that we have much lower oxygen vacancies. It's not zero, so there are probably still some defects or oxygen vacancies, but it's much weaker than you get when you grow at low oxygen pressure. Right? And so here are the transport properties. The sheet resistance as a function of temperature for all these different samples of different lanthanum aluminate composition. They're all conducting. Right? They're all conducting with this something 10 to minus 4, 10 to the 4th sheet resistance at room temperature. And some samples show this kind of upturn, like a condo type of things. So there are probably still have defects with some magnetic properties.
But the one that looks the most stoichiometric has the largest condo signature.
That's the. That's correct. Yes. Yes.
Okay.
That's right. That's the this sample. Let me see.
The purple diamond.
This one.
Yeah.
Yes. Yes.
But I mean, it's the biggest upturn in resistance.
The fact that we grow these at 37 millitorr oxygen pressure and still get them conducting, and nobody has demonstrated before. I think that's because our technique allow us to grow layer by layer films at this pressure and still, make it layer by layer growth. And this is the quantum critical resistance for superconductivity. And I think it's in general consistent with what people have seen. For example, Daryl Schlom's group, that you need aluminum rich to get superconductivity. Right? And, but we get them all conducting, but it does become, the room temperature, the low temperature too, you do get it lower resistance when you go to aluminum rich. And here is the mobility. And these upturn very much related to the mobility. Right? And the room temperature doesn't really change much with stoichiometry, but low temperature does change. And I think the mobility contribute to these temperature dependence mostly. And the carrier density. The carrier density for all these samples is in the order of 10 to the 14th. Right? And it does depend on the stoichiometry, as it should. Right? And here we plot it as a function of the composition. And this is the low temperature data. This is the room temperature data. And this line here is 1.7 minus 2y times 3.3 times 10 to the 14th. And that is what people should expect for films of 10 unit cell with different stoichiometry. It's not 3.3 because it's 10 unit cell. You only get 3.3 when you go to a sufficient thickness. And the dependence on the stoichiometry is because of the fact that when you have different stoichiometry, the charge carried by each layer is different. Right? Instead of plus minus 1, it becomes plus minus 1 minus 2y. And so the amount of charge they transfer to the interface depends on the stoichiometry of lanthanum aluminate. And this is what you would expect, and these are the data points that we observed at room temperature. So these are the other possibilities, and I think we show that we could make the materials without the indication of oxygen vacancies. So I think we could pretty safely exclude that possibility. Bombardment of the strontium titanate, that again will benefit from having higher oxygen pressure during the growth because that thermalizes these energetic flux. And so this will reduce the bombardment. And the interfacial mixing is something that we cannot completely exclude. Right? We cannot rule that out completely if thermodynamics make it such that they will intermix. But on the other hand, in the intermixing caused by the bombardment, that effect, because we are using high oxygen pressure, we can reduce that induced the interfacial mixing. But nevertheless, what we're showing is that if we grow these lanthanum aluminum layers at higher oxygen pressure, we grow these materials without indications of oxygen vacancies, then we can get these kind of dependence of the carrier density on the stoichiometry of lanthanum aluminate, not just quantitatively, but not only qualitatively, but quantitatively. And we think that this is a pretty strong support for the mechanism of these electronic reconstruction. So again, if you ask why other people don't get it and you get it, and I will say that the key difference is that we are able to grow at this high oxygen pressure during the growth, which suppress oxygen vacancies and the bombardment effect, and we are able to grow them still layer by layer, and nobody else could grow with the conventional PLD or laser MBE. And I think this supports the ideas of electronic reconstruction. So in the remaining minutes, I would like to tell you our work on the lanthanum nickelate, and in particular on the metal insulator transition. And we observed that at 1.5 unit cells, and people have attributed this to reduce the dimensionality and strain. And we are saying that oxygen vacancy is also something that we have to consider. And here are some data from literature. This shows that in the whole series of rare earth nickelate series, lanthanum nickelate is a material which is metallic at all temperatures. And but people have found that if you grow it to smaller thickness, this eventually becomes insulating. And this is, I think, the result from Geneva group that shows that these transitions occurred at about 5 unit cells. And then I would ask that when you are talking about the transport properties of films of only a few unit cells, any defects would affect its properties. And how can you guarantee that you are growing materials of, without defects? And so here's what we've done. Again, we use this technique of atomic layer by layer laser MBE. And what we have also found is that we need to grow a buffer layer. We need to grow the buffer layer of lanthanum aluminate. And because we found that however well you treat your substrate, right? There are recipes that you can use to treat these, but it's not good enough. Right? It's not good enough. You need to first put some homoepitaxial lanthanum aluminate buffer layer before you grow the lanthanum nickelate. Right? So these are color coded for all these different layers. So we grow lanthanum aluminate until this intensity oscillation become nice, right? Very nice. And then we start to put the first layer of nickel oxide. And we found that that's important.
Did you say target switching time?
A few seconds, yeah. Well, okay.
It doesn't look like a few seconds on the diagram.
That's by purpose. That's by purpose. And we did find that you need to give it some time to move around and also to get oxygen in.
Does that mean that the old target is still infusing for a while after you stop hitting it?
Well, you can rotate it any time during this time, but the students purposely leave the sample there for some second. And we found that it's important. If you don't do that, you don't get samples as well.
But is that little switching thing the same time scale as the?
Well, no, this is much longer than the time you need to switch.
Okay, but that's not, so this thing at the top is not drawn to scale.
It is to the scale. This is
Well,
switching.
when you say a few seconds, then it looks like you have a few hundred seconds.
Oh, no, okay. So you're right to say that this is not exactly switching time. That should be switching time plus dwell time, or oxidation time, or something. It's not exactly switching. Switching takes about 5 or 6 seconds. And then she just leave it there before she applied the next layer. And she found that is important. That's a very good observation. Here are a bunch of read intensity oscillations for half unit cell, 1 unit cell, 1.5 unit cell layers. And so we get the lanthanum illuminated buffer layer, nice, and then we start to ablate nickel oxide layers, and so on and so forth. And so the question we ask ourselves is, if you say it's 2 unit cell, how do you know it's 2 unit cell, right? So we did the X-ray reflection measurement at synchrotron source at Brookhaven, and we fit it, and the fitting result agrees well with what we designed it to be. We did the cross-section TEM. We can count the atoms, and these are the 2 unit cell layers, and it does look like 2 unit cell, or maybe a little bit more, but it's 2 unit cells. And we do see the buffer layers, and we also can see that the lattice expands somewhat, which is consistent with what we would expect. And so we measure the transport properties of these samples, and this is 1 unit cell, 1.5 unit cell, and 2 unit cell. The half unit cell meaning it's a nickel oxide terminated, right? So different termination. So we find that above 2 unit cells, or even 1 unit cell, it's conducting at all. And once you grow it thinner to 1.5 unit cell, that's where the resistivity shoots up very high. And this is the temperature where this turn happens. And so at very large thickness, it's conducting all the way. But that turning temperature they become higher and higher when you make the film thin. And then the 1.5 unit cell, it's insulating behavior at room temperature. And so this is actually lower than anything that's reported earlier. And I think the Cornell group reported the 2 unit cell. And when I presented there, they were speculating that it probably because we used the lanthanum illuminated buffer layer that they did not. That, of course, provide as perfect as possible buffer layer for the growth of the layer on top of it. What I try to say with these the first principle measurement is trying to say that the first principle seems to suggest that in these materials, grow it under this kind of strain, and even 1 unit cell should still be kind of conducting. It's less conducting than bulk, but it should still be conducting. Yet we do observe that it becomes insulating below 1.5 unit cell. And so one thing that they did not do in their calculation is they didn't really calculate the oxygen vacancies in their calculation. In our the X-ray absorption measurement, oxygen K edge, and we measured this pre-peak, which is related to the hybridization of these P and D orbitals. And what we have found by looking at these the peaks is that there is a feature that develops when we reduce the film thickness. A 40 unit cell completely, well, it doesn't have very pronounced feature here, But when we make it thinner, in particular when it's kind of a 2 and a 1.5 unit cell, that feature develops. And that feature has been attributed to the oxygen deficiency. That's this feature here. Right? If you have, this is a lanthanum nickelate 03, 2.75, and this is oxygen 2.5. And you see this feature become more and more pronounced. And that's what we have seen when the film becomes thinner and thinner. Then we grow, this is 1.5 unit cell film grown at different oxygen pressure. Again, we see that when the pressure becomes lower, this feature becomes more pronounced. So that corresponds to the thickness when we see this dramatic increase in the resistivity and the insulating behavior. So what we propose is that oxygen vacancy is important in this metal insulator transition. Right? Although you could, the reduced dimensionality and strain can make it more insulating, but it's still, it's still metallic until you have oxygen vacancies, which become more dominant around the interface. And that finally drive it to be insulating. Why we see these higher oxygen vacancies at the interface, that's something that we do not have, we don't have evidence to show one way or the other. But we do show that when you approach this interface, you see more and more oxygen vacancies, which turns out to be important for this metal insulator transition. We were also able to measure the orbital polarization, and we see something like 40% of polarization, which is kind of a very interesting for the next step of trying to build something like a high-TC superconductor. So to summarize, I told you that we combine the strengths of MBE and the PLD and to develop this atomic layer by laser MBE, and we believe that allow us to push the thermodynamic boundaries to grow materials further, and we believe that advance the state of the art in growing these oxide materials. So I show you the result of lanthanum leonate on strontium titanate, and because we were able to grow layer by layer at this high oxygen pressure, we could suppress the oxygen vacancy effect, and we show that the behavior of the carrier density is consistent with the electronic reconstruction mechanism. And then lastly, I show you this lanthanum nickelate work that shows that the metal insulator transition in the system is not only the result of reduced dimensionality and strain, but oxygen vacancies is also very important. And the last slides I showed is this large orbital polarization, very promising for making artificial high-TC superconductor materials. And that's all what I have. Thank you very much.
Okay, a few questions. I'm sure we'll have time also, group members, to ask questions offline. But I have a couple of burning questions.
Yes.
So did you look at the insulator to metal transition for the LAOSCO and see the turn on of conductivity above 3 unit cells?
What can I say? I lost, let's say, at least a year's time in doing all this. And that was obviously on my agenda. And actually, we have done the thickness dependence using the compound target. And at that time, we discovered that under a particular set of deposition conditions, we do see this gradual increase. But that's not as nice as doing this atomic layer by layer, which we thought, we are going to do that. That would just complete this story. And then, students graduated, and I have nobody working on this.
Oh, so I have another question. When you looked at these stoichiometric samples, did you, or any of the samples, when you were looking at the transport at low temperature, did you try gating them from the back, and are they gatable?
No, we haven't. It must be the same behavior as the sample you got.
Maybe, maybe not, because depends on.
Oh, I would be happy to give you guys some samples. Well,
Yeah.
no, I take it back. I take it back. The students
You
graduate.
gave us a sample, and then 2 seconds later, you took it back. No.
No, okay. Whoever want to learn a little bit grows, welcome to my group, and you grow it. You take it back. You know, my students, the former students graduate. One great postdoc, yeah, a girl who went back to China. 2 great girls, graduate students, helped develop this technology, and they all left. I have a guy now, and he struggled for a year. And I said, why don't you get one of the former students come back and help you? And eventually, I have to call my students and can you come back for a weekend? She came back, and everything was fine.
I think
To
that
be fair,
answers.
the students left before these new students had a chance to overlap with them. So it was tough, but it takes great care to grow the good sample.
Yeah.
So if you do Xiaoxing analysis,
Mhm.
how many frequencies that you would expect for those LIOL samples? So currently the carrier concentration is
We have high carrier concentration.
much bigger than the
Yeah.
Have you done those magnetotransport experiments?
I think we try to look at them, not on these samples, but on the previous samples that we made from the compound target. I think our carrier density is too high, and it's difficult to see that.
Seeing any nebulization or localization signature?
We don't see any oscillations there. And what do we see? I don't remember seeing anything very particularly interesting, but it's something that if I still had the students, I would be happy to give it to others to measure.
Okay, well, I think we'll have more time this afternoon with Xiaoxing, but let's give him a round of applause. Thank you.
Thank you.